Today we are going to discuss mainly about the chemical equilibrium. And when we are talking about chemical equilibrium, that means we are considering some reversible reactions. So what is reversible reaction? So in many reactions, if you carry out a reaction inside a closed vessel, let's suppose this is your closed, and if you carry out a reaction in which A and B are your reactant, when you mix these two reactants, and let's suppose they will going to give you the product C. Okay, so after some time, uh, though there will be excess amount of the reactant A and B, they will not going to form C. What is the reason behind it? That means you have excess amount of A and excess amount of B. So, and we already know that A will going to react with B to give the C. Okay, so after some time, though they have some amount of A and B are remain in that that closed vessel, they will not going to form C. The meaning of this is that A and B will going to form C, but after some time, from C again A and B can form. So that means the reaction can be C can be formed from A and B. Also the A and B can be again formed from C. So we represent this one by double-headed arrow. Actually it's not double-headed arrow, 100 arrow forward and 100 arrow backward. So this symbol represent the reversibility or the reversible reactions. Okay, for and the upward this arrow represent the forward directions and this arrow represent your backward directions. Okay, so in some examples you may able to see some symbol like that, and this is also a reversible reaction, but here the forward reaction rate will be higher than the backward rate. That means you will get more product than the reactant. Okay, not then actually this rate will be higher than this one. That means this the backward reaction will be very less. Okay, so even you may see this type of symbol, and this symbol represents what the forward reaction rate will be lower than your backward rate. So I hope you understand the concept of reversibility, and mainly faster reactions which are actually fast. If the reaction is very fast, that means if the product will going to form very rapidly, then the reversible case is not we cannot apply the reversible case usually, because the concept behind is that if the reaction is fast, that means A will going to form directly C. It will be you can get a product very in a very little amount of time. So that then at that time, or at that time, at that little amount of time, the seed will not have enough amount of time to again get back into their reactants. That means A plus B. So that's why mainly for fast reactions the reversibility will not going to observed. Okay, so similarly we will not going to observe strong electrolyte. In case of strong electrolytes will not going to show your reversible reactions or reversibility. Okay, so mainly we will going to get reversible in weak electrolytes. As for example, acetic acid, CH3COOH, and ammonium chloride, like that. Okay, but HCl, sodium chloride is a salt, no? So almost all the salt are strong electrolytes. So sodium chloride or the salt will not going to show or exhibit your reversible behavior. Okay, so the first point is discussed. Okay, so what is reversibility? Now also here they define the equilibrium state. So what is equilibrium state? So the equilibrium state is actually defined as, actually it is they actually define as by using the composition of the reaction mixture. So that means at some time, here is, if you consider this reaction, then at some particular time the the forward reaction rate is equal to the backward rate of the reaction. So at that time, what will happen? The forward rate will be equal to the backward rate. Suppose the rate of the forward reaction is equal to RF, okay, and the rate of the backward reaction is RB. So at some time, forward rate equal to your backward rate. So that means at that point no reaction will going to occur because these rates are equal. So we're not going to observe any new formation of new C or any formation of B from C, A and B from C. Okay, so that means these rates are equals. Okay, so at that particular point the composition of the mixture will be fixed. That means no A and B will going to form from C, so A and B will going to be remain same, and no C will going to from A and B, so C concentration will be remain same at that particular point, or at that time where the RF is equal to RB. Understand? So that state in which the composition of the reaction mixture means the reactant plus product, that is the reaction mixture. The reaction mixture is known as, that state is known as your equilibrium state. Equilibrium state. Okay, so mainly if you so we are able to understand the terms equilibrium state. Okay, so here, so what factor will going to determine the equilibrium state? Okay, so actually equilibrium state can be recognized by measuring the pressure difference of that if some reactions occurring, some gaseous reactions occur. Okay, so if some gaseous reactions occur, let's suppose A is a gas and B is also a gas, and it will going to give you gas C. Okay, so when the reaction is occurring, let's suppose A and B are liquid, and it will going to give you C product. Okay, C product, which is a gas. Okay, let's suppose this is gas and A and B are liquid. So when this reaction is occurring, what is going to happen? Gas is forming. That means it will going to expand. Okay, if you put a piston, frictional piston, then it will going to expand. Okay, because of the pressure. So at equilibrium, so that means it will going to expand means, or it will going to give some pressure on that piston. C will going to. Okay, so you can understand by using this figure. Okay, so here you see this A plus B will going to give you what? C. Okay, if this C will going to form, this is, let's suppose this is gas and these two are liquid. Let's suppose these two are liquid state. So when gas is formed, that the volume of the gas is high, so that means they will going to give some pressure. Okay, pressure, and we're going to obtain the pressure difference. Now pressure difference by, if you put a pressure loss here, then you can able to calculate the pressure obtained from that reactions. Okay, so now the thing is that at the equilibrium positions, no gas will be going to new gas will be going to form. Okay, so at that particular point the pressure change will be 0. That means no new pressure will going to, or no additional pressure will be observed. So by observing the pressure, okay, by observing the pressure, we can recognize the equilibrium state, that means equilibrium point. So similarly, even we can say that we can calculate the concentration if the the reaction is liquid state, okay, and the color of the mixer. So in some cases also we can observe the color change. So at the equilibrium, when the reaction will going to finish or not finish, actually at equilibrium state, then there will be no any color change will going to observe. So it is also one example, or this actually this here your parameters, or this tree, by using this tree we can recognize the equilibrium state. Okay, I think up to this you understand. Now we're going to discuss about the actually the law of chemical equilibrium. Okay, so actually we have to derive the law of chemical equilibrium. That means a law which is used, or which is derived for a chemical equilibrium process. Okay, and we have to actually derive that equation from by using thermodynamic concept. But before derivation of that law, we have to know about some basic concept. And before going to discuss about the law of chemical equilibrium, we have to know law of mass action. Okay, so what is the meaning, or what is the what is the meaning of law of mass action? So according to this law, there are mainly 2 points are there. Okay, so this is the 1 point, the 2 points are there. The first point is that the rate at which a substance react will depends on the active mass of it. So let's suppose this is a substance A and this is a substance B. Okay, and they will going to react, let's suppose, and the rate, or how fast they will going to react. Let's suppose the rate at which this A will going to react with B will going to depends upon the active mass of A. Okay, and the rate at which this B will going to react with this A will going to depends upon the active mass of this one. Okay, so that means the rate at which the substance reacts will depends upon their active masses. Okay, so this is the first uh, you know first point of law of mass actions. And the second point is that the rate of a reactions, a rate of a reaction is actually depends upon the product of active masses of the substances, of the reacting substances. So here you see A is reacting with B and B is reacting with A. So let's suppose the active mass of A is A and this one is, let's suppose, B. Okay, so the rate will going to depends upon the product of the product of the active masses of the reacting substances. Okay, so we can understand these things by using one reactions. And here the reaction is your a mole of A will going to react with B mole of B, and let's suppose they form M mole of M and mole of N. Okay, so let's suppose the active mass of this one is A to the power A and this one is B to the power B concentration. Okay, so according to the law of mass actions, what we can say, let's suppose this is rate of forward reaction and this is your backward reaction, this part. Okay, forward reaction rate and backward reaction rate. RF represent forward rate, RB represent backward rate. Okay, so according to the law of mass action, what we can write that RF is equal to, actually this is depends upon so this is depends upon the active masses of A. So how many are present? A mole of A are present, so we have to write here A, and active mass of B to the power B. Okay, so this is your forward reaction rate, and we can this is proportional sign, so we can use a constant of proportional to make it equal. Okay, so this is actually Kf, a constant. Okay, so here B to the power B and this is Rf. and this one is known as, actually k represent, small k represent rate constant, and this is for forward reactions or forward rate constant. Okay, similarly we can write for the backward reaction rate. For the backward reaction rate, this will be what, this product will be act as an reactant, and forward reactant, this for this forward reactions, these are reactant, these are product, and this for these backward reactions, these two are your these two are going to act as reactant, and these are your product. Okay, so that means your backward rate is equal to, so similarly we can write a constant for proportionality, and this is your reactant m to the power m and to the power n. So these two equations is obtained from the law of mass action concept. Okay, so now according to the definition of your equilibrium state, so equilibrium state, at equilibrium state what will happen? At equilibrium state, we know that at equilibrium state Rf is equal to Rv, so that means the forward rate reactions is equal to your backward rate reaction. So what we can substitute the value of forward reaction rate in this equation in the left hand side, and in the right hand side, what we can write, or we can substitute the value of the backward rate. Okay, so this value can be written here, and this value can be written here. So what, let's write the, so just substitute this value. So here in case of Kf, Rf, it will be Kf a to the power a v to the power b is equal to Kb m to the power m to the power n. Okay, so again that means Kf by Kb is equal to your the ratio of forward reaction rate or the n by the ratio of backward rate. Okay, is equal to m to the power m n to the power n b to the power. Okay, and actually this the ratio of forward constant and the backward rate constant is actually known as your equilibrium constant. Okay, so this is equilibrium constant. It is capital, okay, this is capital K equilibrium. So capital K equilibrium, that is equilibrium constant for reversible reactions, is the ratio of active mass of that product by the multiplication of active masses of your reactant. So this is your formula. Okay, and this is actually known as law of chemical equilibrium. So this is important. So this point. Okay, so this is your, so here also they found this one. Okay, so this is your law of chemical equilibrium. So now what you have to do, you have to this is actually just by using the concept of law of mass action we derive this law of chemical equilibrium, but we can also derive this equation or by using thermodynamic concept. So we have to now derive this equation by using concept of thermodynamics. Okay, mainly we are going to discuss use the chemical potential concept. Okay, mainly the chemical potential is nothing but the very important point, actually very important terms, chemical potential, and we're going to see the chemical potential in throughout this chemical equilibrium chapter. Not only in this chapter, also this is very important terms. Okay, actually the chemical potential is related to Gibbs free energy. So how they are related to Gibbs free energy we're going to discuss. Okay, So in next class, we're going to derive the law of thermodynamic equilibrium using thermodynamic concept. Thank you.